Virtualization allows a KVM guest to behave as a hypervisor and launch its own guest. Since being introduced, Nested Virtualization has seen feature additions and optimizations, sometimes hardware supported. This talk is focused on x86 Nested Virtualization, its inner workings and optimizations that make it usable. We'll take a look at some current uses of Nested Virtualization and ponder over the future of this interesting technology with respect to adoption and users. So who here uses Nested Virtualization? That's what? To try out certain things?
Professionally or other purposes.
Oh. Yes. To put your workload inside a jail, I guess?
Not really, more sometimes for simulation purposes and all that. So you need people to train people on different types of hypervisors. Yeah, so you need to test them.
So what do you use?
Multiple machines.
No, for the host hypervisor, what do you use?
Prefer not to say.
What's that?
I prefer not to say, sorry. It's professional.
Only a few possibilities, right? Zen does not allow to
Zen does.
Does?
Yeah.
VirtualBox, no.
I think
KVM,
VirtualBox
yes.
does too.
No.
Yeah, every.
No?
I think
it doesn't work for me. It doesn't work for me. And I can't find the button that enables it.
Well, I could be wrong though, but
Hyper-V, yes, but you have to enable it.
Hyper-V just.
Yes. I'm told yes, but you have to enable it, but in Azure,
But only
it's not
Hyper-V,
enabled.
yes. Not a. I cannot run Linux as a Linux hypervisor inside Hyper-V.
No, I attended a training, they said yes. But I know for a fact in Azure, it doesn't work because probably they have not enabled it. There are only so few hypervisors anyway. If you talk about the Unix, all these things, there are more than that, but most of the company systems, they are only all this, right? Did I miss out anything? Oh yeah, VMware.
VMware, yeah.
I don't know, I think I don't use them. Even like a member of the user group. Okay.
So yeah, so we already spoke about what nested virtualization is. It lets you, or lets the guest run its own guest. So this is of course in the context of KVM only, but yeah, I mean we just spoke about there are a few other hypervisors that can also do this, but yeah, KVM I think was one of the first to implement it. So right now there's nested virtualization on Power, and there's also patches for nested virtualization on ARM. And x86 is pretty stable. When I say stable, when I'm talking about maybe Linux guests. And the reason being that the matrix of the number of guests that you need to test and the number of guest hypervisors you need to test, it could get very complicated. So testing is like a big effort as far as nested virtualization is concerned. And the other problem is specs. So it's a tendency for developers to kind of just shortcut and implement something so that it just works. Now that's fine as far as time is concerned, but what happens is in the process we don't follow the spec. So while KVM can implement something as a quick fix and make a Linux guest work as a nested guest, when you try the same thing with maybe running Hyper-V inside KVM, that won't work anymore because Hyper-V does something different. So I don't know how to explain this, but yeah, I can try, and please feel free to ask questions. So we spoke about the virtual machine control structures, right? So a virtual machine control structure, you can think of it as something that is used by the processor to launch a guest. So here we have the MCS01, which is used by KVM, this thing in red, to launch Zen. So Zen in turn is a hypervisor itself, so Zen might want to run its own guest. So Zen creates its own VMCS, which is VMCS12. Just before that, so in the context of this presentation, or for nested virtualization as well, we usually refer to the host hypervisor as L0, the one after that is L1, the one after that is L2. So So Zen creates its own VMCS to launch a guest, which is VMCS 1.2. So how does nested virtualization work? Because this VMCS over here cannot run directly on the hardware or the processor that's on the hardware. Zen cannot load it directly. So what happens is when Zen creates this VMCS that gets trapped by KVM, and KVM knows about this VMCS now. So what it does is it tries to create a subset of a new VMCS based on this VMCS over here and the VMCS that it has used to create Zen. And the reason it tries to create a minimal subset of the two is because it doesn't want this guest to have more features than Zen has. So you want the minimal kind of intersection of the two. And then it creates a new VMCS called VMCS 02 that I have not shown in this figure, and then loads that VMCS to launch Linux. In the context of Zen now, it thinks that it has created this new guest, but in reality what is happening is that operation gets tracked to KVM, and then KVM actually uses that information to create a new VMCS and then launch Linux on behalf of L1. And then what happens is, just like we spoke about the VM exit that has to happen so that both the guest and host makes progress. So in this case, we have to have exits between all sorts of exits, like L1 to L0, L2 to L0, then back from L0 to L1, then back from L0 to L2. So everyone has to make progress. So in this way, everyone steps forward little by little, and then Zen thinks that it has its own guest because KVM or the host hypervisor always makes sure that the state of the VMCS 1.2 over here is always in a state that makes Zen think that it owns Linux or L2 and L2 is progressing. It's a little bit, I hope I made it clear, although, but that's how it is. So as I mentioned in the previous slide, the main cost, even though this is hardware-based virtualization, is the huge number of exits. So if we go back, as I said, for example, let's assume that L2 is running right now, and then something happens. For example, we have to make sure that this guy over here has to make progress. So the way it makes progress is, for example, by making sure that KVM injects a timer interrupt, which is regulated every second, for example, or every 100 milliseconds. So what happens is you exit out of L2 to L0, and then at this point the VMCS that is being used to run L2 is loaded onto the processor. So that gets removed, and then we now load VMCS 01 again. Then we inject something called a virtual interrupt, and then we run Zen now. Now when Zen runs, it sees the interrupt. Now to actually handle the interrupt, there has to be a new exit again. So then you again exit from L1 to L0, and then KVM does all its work so that guests can see the L1 can see its new interrupt, and then jumps back to L1. At some point, again you jump back to L0, and you have to jump back to L2. So what we call this as like a huge number of VM exits that are happening that multiply again and again to be able to run nested virtualization, and that actually makes it really, really slow. Even though you are actually using the VMX extensions on the host hypervisor. And the way to kind of optimize on that is, so this is known that not a lot of, this guy does not need to know a lot about L2. Or maybe he can actually know about a lot of things about L2 at a later stage when we have to enter L1 and run L1 itself, because as long as we are running L2, we are not running L1, so we don't have to tell it about everything that L1 is doing in terms of a change that could affect the change to this VMCS. So what we do is, for a lot of cases, we just exit to L0 whenever an event needs to be handled. We do whatever changes we need to do, and then we jump back to L2. But we keep track of the changes that needs to be reflected in the VMCS that L1 has, and the next time we actually run L1, we make those changes to L1 so that L1 can see it. In that way, we actually reduce the number of VM exits and both of them can make progress at a comfortable pace. So that this is a slide that explains that, these are some of the features that are currently implemented, not specifically in KVM, but I'm pretty sure there are similar implementations for other hypervisors, but they do help with nested virtualization. So one thing is nested EPT. Now, extended page tables or EPT is a hardware provided mechanism to provide 2 levels of page translation, which helps with just 1 level virtualization. So when a guest is doing its page translation from the guest virtual address to guest physical address, we have corresponding EPT page tables on the host that actually translates from the host virtual address to host physical address. So everything happens in one go, so you don't have to use shadow page tables. That was the standard for page translation with virtual machines. So nested EPT is a way to optimize on using the EPT hardware for nested guests. And the way this happens is every time the level 1 guest actually tries to create page tables or EPT page tables, L0 or the host hypervisor will trap that operation, and it will create its own page tables on behalf of L1, just like we spoke about the creation of VMCS. So now this translation over here actually is happening inside EPT from this point to that point. So the nested guest virtual address to guest physical address happens with the standard page tables, and the EPT translation happens between nested guest physical address to host physical address. A lot of this is probably not very intuitive, but yeah, once you kind of look at the code and try to understand, I think it should be much more clear. And the performance benefits are actually very good. For example, kernel compilation with just plain shadow page tables for nested virtualization is 34 minutes, but with nested EPT it's 10 minutes, so it's quite a performance improvement. Shadow VMCS is another hardware provided performance related feature. So what Shadow VMCS does is it lets the host hypervisor create a new VMCS besides the one that level 1 is using, such as VMCS 1.2. So what happens is this is just a shadow, which means that when the level 1 hypervisor tries to access this VMCS, there's no VM exit at all. Because this is a shadow, and the host hypervisor knows that this is the host processor knows that you're not supposed to exit. Whenever there is an exit back to 0, the VMCS sync, the shadow VMCS and the GL VMCS syncs, and then the changes get reflected in the new VMCS that L1 is using to run L2. So again, this is also something that helps with good performance numbers. Without VMCS, there is a certain amount of improvement. Then the next is preemption timer. So a few slides back, I spoke about the timer interrupt, which happens every few milliseconds, and that actually is a performance cost. So instead of doing that, the host hypervisor can set up a preemption timer that is set for a specific amount of time, and then once the timer expires, whatever you're running, for example, you're running L2, you exit back to L0, then the host hypervisor can decide to run L1 for a while and then again set up a timer. So that way you don't have to exit on every timer interrupt. This also results in lesser number of exits from L2 to L0 and L1 to L0, and of course improves performance. Interrupt acknowledgement is basically a way to write the interrupt information in the VMCS so that you don't have to inject a virtual interrupt. So what happens is, for example, there is a key press and you need to inject that interrupt to the guest because it's the key press for a window inside the guest. To do that, what you have to do is you have to see something called as an interrupt window. And to do that, you have to inject a fake interrupt first of all to the guest, and once the guest receives that fake interrupt, then you have to inject a real interrupt so that you can actually see it. Instead of doing all this that requires 2 VM exits, you can actually just write the VMCS, the interrupt info into VMCS12, and the guest can see it. And the reason why that was not implemented as a standard is because this came on later, after VMX was introduced on more later processors, and so. But these days, all hypervisors actually use interrupt acknowledgement, and this actually saves on a few number of VM exits as well. And then nested virtual processor identifier is something. So VPID is something that the processor uses to tag guest address spaces, and this is also something that you could use to improve performance for nested virtualization. Previously, what we used to do was we did not advertise VPID for the level 1 hypervisor. Instead, we used to share a single VPID identifier between L1 and L2. And if you invalidated this specific tag, then all the address spaces were kind of invalidated. But now what we do is we have a VPID for all level 2 guests, and every time the level 1 guest is actually switching between these level 2 guests, we invalidate. The advantage of doing this is that now L1 can have its own VPID, so you don't invalidate those address spaces when you have to invalidate level 2 guests, because the assumption is that level 1, at least in the context of nested virtualization, level 1 is more kind of consistent, stays there, but level 2 kind of comes and goes. So that way you don't have to have the performance impact of having to recreate all the cache entries for VPID. These are a few more that are already MSR load store and nested APK is already implemented, but not nested IO menu. MSR load store is also again a hardware enforced way to load all the MSRs in one go and then save them in one go whenever you exit. Nested APK is basically a way to not exit when the level 1 hypervisor is trying to access the APEC or the local APEC. And then nested IOMMU is of course a way to have device assignment for nested virtualization. So these also improve performance by letting you directly access devices from the host in the nested guest, and also reducing VM exits. Setting up nested virtualization is very easy. And first, you just have to. It's not visible again. I'm so sorry about that. But you just have to modpro KVM Intel or KVM underscore AMD. Setting nested is equal to 1. Although with AMD, nested is actually enabled by default, so you don't have to actually do it. And then the main thing that you have to do is, whenever you run QEMU, you have to advertise the VMX flag to the guest, so the guest actually sees a processor that actually has virtualization extensions. And then, of course, this actually can extend up to many levels because of the way it works, of course, but no one actually tests it to many levels. They just use 2 levels or 3 levels of virtualization.
So is this the kernel module parameters or the kernel parameter?
The one at the top is the kernel module parameter, and this is what you use to run QEMU. So some of the use cases, so most of the times people, this is more kind of like a fancy feature rather than having any specific use. Most of the people use it to test some quick setups. I know inside Red Hat people, OpenStack people use it a lot to simulate all the controller nodes and all that stuff inside one single machine. They have a script that just sets up everything, and then they test run whatever they need to test, and then just destroy everything. But these are some of the things that I can think of. For example, every operating system these days is a hypervisor. So if you want to get the most out of your OS as a guest, you need nested virtualization. Cloud providers can, of course, let users run their own guest. Although I don't know if any actually lets you do it yet. I know Google actually contributes a lot to nested virtualization lately, so maybe they might have something, but I'm not sure. There are some hardware extensions that are actually rely on top of VMX, so if you want to use something like them inside a guest, then of course you need nested virtualization. And then of course there's the regular testing and debugging, and then exploit and understanding or researching hypervisor exploits are of course common use cases for nested virt. So this is more kind of a common slide for how to contribute. Unfortunately or fortunately, I don't know, but it's in a pretty stable state as far as KVM and QEMU is concerned. They are pretty stable these days, but that doesn't mean that they don't need help. For example, nested virtualization itself has seen few testing efforts. So I'm pretty sure there are so many bugs out there where you are not running a Linux hypervisor. And just recently we actually finally fixed able to run Hyper-V as a hypervisor inside KVM, although even running that to the best of its kind of performance abilities or something has not been tested fully. And most of the development happens on the mailing list, which is probably not as scary, I don't know. You can also report bugs to the Bugzilla, the kernel Bugzilla, which is bugzilla.kernel.org, or you can actually check the bugs over there and submit a fix. And we have a somewhat out-of-date wiki, which is linuxkvm.org, which is this is for KVM, and then we have a wiki for QEMU. Of course, if you are willing to help with documentation, you can definitely use try to contribute to the wiki. And QEMU has been participant with Summer of Code and Outreach for a few years now. Although you can also find projects on KVM and libvirt and all that stuff, everything under the QEMU umbrella. So if you're a student, you'd like to kind of participate with new things on KVM or QEMU, you can definitely check out Outreach and Summer of Code. These are some of the references if you want to study further. And I think that's it. Do I have more time?
I think 5 minutes or so.
Oh, okay, 5 minutes. So maybe we can just, if you have any questions. I wanted to take a quick look at the code so that you could kind of get a feel of whatever I was trying to explain, because sometimes looking at the code makes it easier. All the explaining about how you jump back and forth between those guests, it's something, either it's animated or you look at the code. I mean, I know it's not easy to kind of just say it to someone and get it.
So all these improvements, right? Which version of the kernel?
I'm sorry?
All these improvements you talk about, which version of the kernel?
They are all upstream.
Yeah,
Everything is upstream.
Which version?
Any version that you pick up right now. I think if you pick up anything that is later than 4.1, you can find everything.
After 4.1?
Yeah.
So from what I understand, right, is what they talk about, the host hypervisor doesn't need to know anything about the hypervisor, the virtual hypervisor running, virtualized hypervisor running within it. Is that correct?
Rather, it's the other way around. In a way, the nested hypervisor doesn't have to know a lot of things about the guest it's trying to run, because the host can take care of all the operations. And if the nested hypervisor complains about something, and KVM can, or the host hypervisor can make sure that, okay, the nested hypervisor might want to see the state of this VMCS bit in a specific, this should be 1, and then the host hypervisor can just set it to 1 before actually it runs the nested hypervisor. So it's the other way around. The guest hypervisor doesn't need to know a lot of things about how it's running its own guest, because in reality it's not running it. It's the host hypervisor which is running it.
Okay, so the host hypervisor Okay, very simple question. Does a host hypervisor need to understand the nested hypervisor?
Yes, it does. So that's why I wanted to.
So it works only with specific nested hypervisors.
As long as you are following the spec, everything should work. Because whenever if you're a nested hypervisor and you create whatever you are doing it in the VMCS. And the host actually knows about the VMCS. The host actually knows about the VMCS that the guest hypervisor has. So it can do anything with that VMCS. Because this is all in an area of memory which is actually something that the host knows about. The host gave this memory area to the nested hypervisor, right? So the host actually knows about everything. It doesn't have to be hypervisor dependent as to, and the structure of VMCS is a standard. It's Intel specific. So no matter if you have Hyper-V or Zen or whatever you have, the structure of VMCS has to stay the same as long as you are trying to support. You are trying to say that you are Intel supported or your hypervisor supports Intel processors.
Okay, so if I may ask one last question, with all these improvements, like how much performance penalty there still is?
Depends on the numbers that I had for what the numbers that I had from my last presentation. Depends on what. So right now, though, if you are running something which is purely CPU intensive, like a kernel compile or something, you could get as close to 96 or 97% of what you get on bare metal.
CPU intensive, that means
like kernel compile, for example.
That's user time, right? 90%, 90 what?
96, 97.
That's user time.
Yeah.
And if you got what about this kernel thing with I/O?
If you have I/O, then of course it suffers because everything is kind of nested as far as I/O is concerned. No one has yet looked at the I/O side and how to efficiently kind of pass through some of the things directly to the level 0 hypervisor.
VTD helps with that.
Yeah. So one of the things is VTD. So that's something that is a work in progress, which is nested VTD. That way you could directly assign an external device from the host back just directly to the level 2 guest.
VTD, you're talking about the IOMMU, which is SRVIO?
No, SRIO is different. VTD is just for device assignment, or IOMMU.
VTD is not the same as SRVIO? No.
SRIOB, no.
SRIOB takes your PCI address space, or PCI functions, PCI virtual functions for device channels. VTD is address space.
Yeah, I mean, it does help with virtualization, but it does not do the assignment. It lets you kind of, let you use the same hardware device among many different many different guests. Yeah.
So are you going to go toward like parameterized hypervisor, or you will somewhat change the specification to get better performance?
Yeah, we do that. I mean, it's unfortunate, but we do that. And the downside of it is, for example, if you run VMware, ESX has nested virtualization, but you could see in the logs that it will identify, oh, this is not a ESX guest. Okay, I'm just not going to use EPT. I'm not going to use this, and I'm not going to use that. And every hypervisor does this because for them it's more kind of like a fancy thing that everyone has to implement because everyone has it. As long as I think there is no real kind of industry demand for it, people are just gonna sidetrack and just not use any specification compliance. So
I think also on ARM it's basically impossible to follow the spec. Because you can't nest hypervisors, you can't put the correct traps because you do this.
Right, and so the ARM work is actually by Columbia University. They just posted a math series. I'm not very familiar about how they're trying to do it, but I do know that it's on a very recent processor, very recent ARM 8.2A or something, which is not out yet. So they're using the ARM simulator. I don't exactly know how they are taking care of the specs and.
ARM64 has.
Yeah, but you can't nest it because some traps aren't available.
Right. Yeah.
Yeah, exactly.
Supervisor rather than
There are maybe some new enhancements in the new version of ARM processor, and maybe that's what they're using, but I'm not sure. We're done?
more questions?
Actually, does QEMU silently fall or heuristically fall back to binary translation if it detects that Nested DBT is slower, or is that still?
Well, that's a good idea.
So VMware does that. VMware does binary translation as well as hardware-assisted virtualization.
Like a fallback?
Well, yes, it has a heuristic to detect. This the next X instructions would be faster to just run in software than to go past the computer.
No, QEMU doesn't do that right now. But that's a good, that's a good thing.
That's part of their secrets also.
Okay.
Okay, round of applause.
Thank you.